Hey everyone, today we are going to solve LeetCode problem number 2385. It has been asked in many companies like Amazon, Microsoft, ShareChat. So let's have a look on this problem statement. Amount of time for a binary tree to be infected. Okay, in this problem we are given a root of a binary tree with unique values only and an integer start, okay, at minute 0 and infection start from the node with value start. Okay, and each minute a node become infected if the node is currently uninfected and the node is adjacent to the infected node. Problem says that in this problem the infection is going to start from the start node, start value. Start is an integer given to us and there are only unique values. It means we are going to have only one start. From that start, in every minute it is infecting its adjacent values. Let's say at time 0, 3 is infected. At time 1, this 1, 10, and 6 will get infected. In 2 minutes, this 5 node will get infected. In 3 minutes, this will get infected. And in 4 minutes, this 9 and 2 node will get infected. And we have to return the minimum number of minutes needed for the entire tree to be infected. Okay, so this tree will get infected in 4 minutes because we need at least 4 minutes to make this tree infected if we are starting from 3. So in short, what we have to find is we have to find the farthest node from this start node. This is our start node and we have to find the farthest node from the start node. These two are the farthest node and the distance to the farthest node is 1, 2, 3, 4. It means 4 minutes we will take. So how do we solve this problem? The first approach can be if we convert this tree into a graph, because on the tree we have this node and we have two pointers only, pointer to the left child and to the right child, and we cannot go to the parent. But if we convert this tree to an undirected graph, it means there won't be any edges. We can go to left, go to right, and go to parent as well. From parent we can go to this node. There is no arrow in it. So if this tree get converted to the graph, undirected graph, it means in that case what we can do is we can start our BFS from this node. On the first level we have this node. On the second level we will have these three nodes. On the third level we have this node. This is on the fourth level. This is on the fifth level. Okay, then ultimately what we can do is we can return level -1, which is going to be the minimum number of minutes needed to make this tree infected. Okay, so hope this approach is clear to you. In this approach we are just converting our tree to undirected graph, because if we convert this to the undirected graph we will be able to approach in a BFS way and we can apply the BFS over that adjacency. So this undirected graph, how we will represent this graph? We can prepare an adjacency map where it is mapping the node and the like neighbor. So let's say this is our graph. Here how we are going to prepare the adjacency. In the adjacency matrix we are going to map an integer. Let's say in this case if I start with 3, I'm going to map 3 against its neighbors, set of neighbors. Which are all the neighbors to this tree? 10, 6, and the parent as well. So 10 is the neighbor, 6 is the neighbor, 1 is the neighbor. So this is for 3. For 1 we have 5 and 3. But for 1 we don't have any neighbor. Okay. So if you want to like if you have to introduce the neighbor or maybe the parent in the problem, you can have any value which is not from this. No, because node values are going from 1 to 10 to the power 5. So let's say the one is going to have a neighbor of 0, which is an arbitrary node. That will not going to store in it. So our map keys, these are keys. Keys are going from 1 to 10 power 5 only. So 1 have a adjacency neighbor to 5 and 3, and 4 are having neighbor 9 to 5. Okay, and 9 is having 4, 2 is having 4, 10 is having 3, 6 is having 3. So this is something our adjacency. We have 3 neighbor of 3, 1 neighbor of 10, 1 neighbor of 6, 2 neighbor of 1, 3 neighbor of 4, and 1 neighbor of 9 and 2 each. Okay. Once we have prepared our adjacency, we can easily start the BFS using our start node. Which is our start node? 3 is our start node here. So 3 we will add to the queue, and this is going to be our first level. Now I'm going to add all the neighbors of 3. I have pulled out 3 and added 10, 6, 1 into the queue, and also mark them visited. It is visited, 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 visited. Okay. Now this is my second level. From 10, 6, 1. 10 does not have any neighbor which is unvisited. Okay. 6 does not have any neighbor which is unvisited because 6 is already visited. And for 1 we have 5 only. For 1 we have 5 and 3. 3 is already visited, so we will not add that. Okay. So this is my third level, and which is my fourth level. I will process, these are used. I will process from 5. 5 is connected to which node? 5 is connected to 1 and 4. So 5 is connected to 1 is already visited. I will add 4 in it. So 4 is going to be my fourth level. And after 4, 4 is connected to 9, 2 and 5. 9, 2 both are unvisited. So I will add 9 and 2 in this. So this is going to be my fifth level. So this is at time 0, at time 1, at time 2, at time 3, at time 4. At time 4, we are infecting all the nodes. So minimum time taken is 4, equivalent to the levels. Okay, so this was our first approach, like converting a tree to the undirected graph and then performing the BFS over that and calculating the levels. BFS you can prepare using Q. Okay, let's first code this approach. And what is the time and complexity for this? What is the time? From tree, we are converting it to graph. That is adjacency. For that, it is taking O of n. And from adjacency, I am performing BFS. BFS is also going to take O of n time. N is the number of nodes in the tree. Okay. So ultimately, it is n plus n, 2n. And what is the space complexity? Space complexity will also be O of n in the order of n, because we are taking Q, and also we are taking map here. So both time and space are in the order of n, but the interviewer can ask, instead of having two passes, can we do it in a single pass? Let's say in my tree, if I make only one iteration, and can we do that in one iteration? That will we will have a look in my second approach. Before that, let's code this approach. Here, first of all, we have to create our adjacency from this root. For that, I'm taking a map of integer and set of its neighbor, which are integers. Let's call it adjacency new hash map. Now I'm going to write a convert function which will convert my tree starting from this root to this adjacency. And you have to see that when we are at 3, we will add both of its neighbor, but we cannot have a pointer to its parent. So for that, if we are making call from 1 to 3, we have to pass the parent value. But 1 do not have any parent. So our node value are going from 1 to 10 power 5. So if I pass the 0 as a parent, I can add a manual check. If I'm getting 0, it's not a valid node. Okay, this is my parent, and I'm also passing the adjacency. Okay, now first implement the convert function. I'm passing parent because the tree is having arrows downwards, not upwards. Private void convert. This is my convert function. I'm passing root value, parent value, and map value. Let's implement this function. First of all, if the root value is null, what do I have to do is I will just directly return. I don't have to do anything. Nothing should be stored in the adjacency. Now I will check whether there is already an entry in the map against root.value. If map dot contains key root.value. Note, if map does not contain the key root.value, I will put another entry against root.value, because in this entry I'm going to add two children, maximum two children or parent. Let's extract this set. Map dot get root dot value. This is my set which I just inserted if it is not already present. So in this set I'm going to add the values of parent and the left child and the right child. So I will add the value of parent if it is not 0, because 0 is not a valid index. If parent not equal to 0, it means I have a valid parent. So I can add that parent to the set. Now for the left part, root dot left not equal to root dot right not equal to null. If left is not null, I'm going to add set dot add root dot left dot value, because our set is of integer type. Set dot add root dot right dot value. I have added all the neighbors. Now what I have to do is I will just make recursive call to left subpart and the right subpart to add values to the adjacency. Convert root dot left with parent as root dot value and this adjacency, and the right part. Okay, now my convert function is completed, and here at this point I have my adjacency list totally filled with all the details. Now I can add this adjacency as a graph and I can do the BFS over that. So for BFS, first of all we have to add the root value, and before that I have to add q of integer new linked list, and q dot offer start visited dot add start, because it is a graph. So for visited I am taking a set, and for level just directly take a minute variable. Minute is 0 in the starting. Q dot offer start value is visited. I have taken a q for my BFS and set to track over that. Let's call this visited set. Okay, now I'm starting my BFS while the queue is not empty. I'll capture the length q dot size while length minus greater than 0. Okay, but after processing this level I will add my minute, and in the end what I have to return is minute minus 1. Okay, here process each element in this level. So int remove equal to q dot poll and iterate over each neighbor. Let's say for int v adjacency dot get remove For each level, for each neighbor, we'll check whether it is visited or not. If it is not visited, contains v. What I'm going to do is I will offer that v value in the queue and mark it visited. We are on the first level, taken each element, added the neighbors, and then incremented the level. Okay, I hope it is done. Let's try to test our sample test cases. Compilation error. What we are missing? There should be one bracket only. Okay, test cases are passed, submitting the problem. This is submitted successfully. Hope you understood this approach. Let's move to the more advanced approach, which is doing it in a single iteration using DFS. So in this approach, we are going to start from this start node and we are doing DFS instead of BFS. So we have two possibilities, that whether our answer belongs to this portion, or the second possibility is that whether our answer belongs to this portion. So this is first portion, this is second portion. And what we have to find is, we have to find the farthest node. We have to find the farthest node from the start value. Let's have a look on the first section first. Here we can easily see that the start value is our root, and from root, if we have to find the farthest value, what we are going to do is we will just calculate the height of this left portion and height of this right portion. Whichever is the bigger one, that will be the answer. Let's have another example. Let's say we have 1 2 3 4 6 and here 5, and let's say start value is equal to 1. So here we can easily see that this is our start value, and here we have to find the time in which the whole tree will get infected. So we can directly calculate the height. From the left side it is 1 unit, 2 unit, 3 unit. For right side it is 1 unit, 2 unit. So it will take minimum 3 minutes for the tree to get completely infected. So it means we just have to calculate the height of the left portion and or right portion if the start value is at our root. Okay, now first portion is clear to us. And how do we calculate the height? That is just like a normal DFS call. In the last root node, we are calling left side, right side. From both sides we are getting 0 height, and 0 height maximum is 0 plus 1 is 1. Left side it is getting 1, right side it is getting 0. So maximum is 1, 1 plus 1 2, height 3. And here height is 1, height is 2, height is 3 and 2, maximum is 3. 3 plus 1 4. So 4 is the height. Okay. So in this way we can calculate our answer if that the start value belongs to the start node or root node. Okay. But the tricky part is, how do we calculate this portion? So for this portion, this is the root, and from the left side we can easily find the height. Let's say height is h1. Okay, and from the right side what we have to figure out is, we have to figure out the height till the start value, which is h2. So let's say we have the left side height, which is h1, which should be something like positive 4, and the right side we have h2. So the magnitude of h1 and h2 should be our answer, can be the candidate to our answer. Okay, so the one candidate is this h1 plus h2. This is second one. The first candidate is maximum of height of, this is, let's say this is called HL, height of left part, height of right part, height of left or height of right, maximum of HL or HR. This is one candidate to our answer. This is second candidate to our answer. The maximum of this and this will be our final answer. Okay. So for the first section, it is definitely clear to us that we have to just find the height in the binary tree. For the second portion, from the root to left, we can easily find the height. From the root to the start node, we have to do some kind of trick. Okay. If I directly share the height from this third as well, let's say for 3, the height, the depth is 2. If I'm passing 2, that will not make any sense. So what I'm going to do is, we will just return the, from 3, we will if we encounter the start value, we will start returning a negative depth. Let's have a cleaner look. From 3, what we will return is, we will return the negative, we will start returning negative value of depth. From the left side, we know the depth, which is 3. From the right side, if I'm returning -1. So at root, how do we distinguish that whether we are in this section or in this section? If we are in this section 1, the left height and the right height both will be positive. Okay, so this is our first section, and this is in the second section. In the second section, the left height and the right height will be of opposite sign. Either this can be negative or this can be positive. This is positive or this is negative. So by this we can get to know that this is from first section or second section. So if both are positive, then we are good. Then just directly get the left height, right height plus 1. Or we are at root. If we are at root, we will get another candidate to our answer. Okay, let me repeat again. We have two sections. The first section is that our answer coming from here, and the second section is our answer coming from here. If our answer is coming from here, it should be left subtree height, right subtree height, or you can say depth. That should be the answer. Let's say left height is equal to 1, right height is equal to 1. So 1 is our candidate answer. So 1 can be the possible answer to our question. Okay, in the left part, the depth of the left subtree is 3, and for the right side it is 1 till start node. Root to start is 1. So 3 plus 1 is 4. So 4 is our second answer. As we can see that 4 is very big than as compared to 1, so 4 is going to be our answer. So our answer going from this 3 to 1, and then 5, 4, 2 or 9, like this. Okay, so for this section, our left height and right height will be of opposite sign. In this section, it will be of same sign, and at this node we will just have to add one option to our answer, that this one. Okay, if we have a look at the code, we'll get more understanding. Now if you have a look at the code, we are having 3 cases. The root value is the start value. Let's say we are at 3 as per the above diagram. If we are at 3, we have one candidate to our answer. Okay, which was the left subtree and the right subtree depth. Let's say it is left depth and it is right depth. So maximum of this can be one possible answer. Okay, so for that I have captured here. And from here, what I'm going to return is, we will return the negative height. Because at any position, let's say at 1, we will get to know, let's say from here it will get 3, from here I will get -1. At 1, which is the root node, I will get to know that Anyone is the negative. It means this can be the possible path to our another possible answer. From 3, it means from 3 to root there can be a possible answer. So when both are so our first case was root is the value start. So we are here. We can possibly capture left depth, right depth, the maximum of both. And the second option is both are positive. Left depth and right depth are positive. If both are positive, that we are under this, let's say under left subtree, under right subtree. If we are not having start, we don't know like what is the accurate answer. Our answer should start from this node only. If we are running in the left portion only, right portion only, we don't have any answer, so we are not capturing anything. We are just capturing the left depth with the same logic, that maximum of left depth, right depth plus 1. If we are at this portion, let's say we are at root, we have two type of depth. One is positive, one is negative. It means this can be the path to our answer, and we have to capture the value. From one side it is positive value, let's say it is positive a, it, and this is the root, and from side minus b. It means this minus b is definitely starting from start. So minus a plus b, the magnitude of both. The magnitude value, absolute value of minus b is b, absolute value of a is a. So this can be the possible answer. So this is also possible way. So absolute value of both can be the distance, and updating that distance to the maximum value in the same way we are updating here. After that, what depth do we have to return is the minimum of these two. Let's say minimum of 3 and minus 1. What is the minimum? Minus 1 is the minimum, and making it minus 1 to minus 2, we have to subtract 1, so it is minus 2. So let's say if here we have some other root 8. 8 is the parent of 1. So from 8 to 1, let me draw again. 8, 1, from here it was 3. From root 3, the height was minus 1. It was depth was minus 1, depth was 3, and something like this. So at 1, we captured this path, and we are moving ahead and passing the depth further. So if we have to pass the depth, so our path is definitely going to start from this 3, and we will go something like this. Like this. It means we have to capture this depth only. And this depth only we have minus 1 from 3 to 1, and from 3 to 8 it should be minus 2, right? Because minus we are taking to to specify that the start value is here in this subtree. Okay, so to make minus 1 to minus 2, I am subtracting 1 again. So that's why I'm subtracting 1 in my code. So we got three possibility. If the root value is start value, we just capture the possible answer. Otherwise, we don't have the answer, just process the depth. And third possibility is our start value is present either in the left side or the right side. Just capture that value and update the depth. To update the depth, we'll just have to get the minimum value minus 1. So making it minus 2 from minus 1, like this. It was a bit tricky and hard. Okay, let's try to code this as well. Let's also have a look at the time and space complexity for this. For time, we are only iterating our tree one time. It means order of n. In the BFS approach, it was order of n plus n, which is 2n. And what is the space complexity? Let's say we got a very bad tree in the form of linked list, improper binary tree, which is making a recursion stack of size order of n. So in the worst case, the time is going to order of n, and the space is going to order of n. So what did we improve? We just saved one iteration. Let's code this approach. I have written another function to capture the result using DFS. Here I'm writing a solution function. For me, this solution function will keep on updating the maximum distance. This is the maximum distance of any node from start node. Okay, let's implement this function. Public int solve function. If root is null, we are returning 0 depth. Otherwise, we will capture the left depth and the right depth. Here comes the main logic. If root dot value is equal to start, or else if both the heights are positive or depth are positive, left depth is greater than equal to 0 and right depth greater than equal to 0, and the other else is that one is positive and one is negative. If we are starting from, if the root is the value, it means we'll capture in a simple way. The maximum distance is equal to math.max, and from here we will keep on passing depth in the negative form to the parent. Okay, so we have captured maximum distance. We are definitely going to have that path where on the root one height is negative, one depth is negative, one depth is positive. So we can directly put this value in the maximum distance. And if both the heights are positive, we will just update the depth to math dot maximum of left depth and right depth plus 1. And the main condition is this: int, let's say distance is equal to math dot absolute left depth plus math dot absolute right depth, and update the maximum distance. Now what should be the depth here? Depth is equal to math left depth or right depth. Let's say we got -1 and now we'll add another -1, and in the end from this function we are returning depth. Okay, so this is my solution function updating the maximum distance. Root is null, returning 0 depth, left depth and right depth from left subtree, from right subtree. If root dot value equal to start, we will just capture the maximum distance which is left depth or right depth, and depth will get negative. If both are positive, it means we are under the start node, either in the left part or in the right part. So for that we'll just update the depth. Otherwise, let's say we are at 1. If we are at 1, we will capture the distance. From the left part, it is left depth. From the right part, it is right depth. We are using absolute because one of the height or depth is negative. And then this is a candidate to the answer. So we will compare its value with the maximum distance and update the bigger value in the maximum distance. And then we will update the depth to further adding -1. Okay, let me run over sample cases. Okay, it is working fine. Submitting the problem. Submitted successfully. It is slightly improved version where we are only making one iteration instead of two. Okay, I hope you understood the problem. Thank you guys. I'm attaching the code below in the description.